Hello viewers, in today's class we are going to discuss one important inequality with the help of Lagrange's mean value theorem, right? So viewers, we have already discussed a lot about different type of inequalities which can be proved using the famous Lagrange's mean value theorem. So in this class, we'll see this problem in which we have to show that this inequality holds for x greater than 1. Right? So the inequality is e raised to x greater than the product of e and x, where e is the famous Euler's number, right? So let us see how nicely we can prove this inequality with the help of Lagrange mean value theorem. And moreover, we can also prove this inequality with the help of the concept of increasing and decreasing functions, right? So there may be two methods here, but here we'll prefer the method by Lagrange's mean value theorem. So let us start. So here we'll apply the conditions of Lagrange's mean value theorem to a function, right? So let us first see how we can construct or frame a suitable function. So here e raised to x greater than e times x we have to prove. So we can form a function, say f of x is equal to e raised to x minus e times x, right? So we can say that if we take e times x to the left hand side, we'll get a term like e raised to x minus ex, right? So this is our function, right? And now we'll apply Lagrange mean value theorem to this function, and here the interval we can take 1 comma alpha, right? So this is the interval in which we have to apply Lagrange mean value theorem to this function, where this quantity alpha is greater than 1, right? So now the first condition of Lagrange's mean value theorem is the continuity of this function f of x, right? And now here we see that f of x is made up of two functions. This is e raised to x and this is a continuous function, because the exponential function is a continuous function in its domain, and here we are taking 1 comma alpha, where alpha is greater than 1. So obviously this function e raised to x is continuous in this interval, right? And e times x, e is a constant and x is a polynomial, right? So e times x is also a continuous function. So ex being a polynomial function, this is also continuous. So fx is now a sum of two continuous functions, and we know that if a function f of x is given like this, g of x plus h of x, and g of x and h of x are continuous functions, then the function f of x is also a continuous function, right? So the first condition is satisfied. Now let us come to the second condition. So now if we differentiate f of x, then we'll get f prime of x is equal to the derivative of e raised to x minus ex, and the derivative of e raised to x is e raised to x, and here the derivative of x is 1, so we have simply e, right? So f prime of x is equal to e raised to x minus e, and this suggests that the derivative is it exists for all values of x which belongs to this interval, that is open interval 1 comma alpha, right, where alpha is greater than 1. And in the first case, the function f of x is a continuous function in the closed interval 1 comma alpha, where alpha is greater than 1. So the two conditions of Lagrange mean value theorem are well satisfied by this function f of x, right? So now this function is continuous and differentiable. So Lagrange's mean value theorem says that there must exist some point x is equal to c, where c lies between 1 and alpha, right? So c is greater than 1 and less than alpha. So Lagrange's mean value theorem says that once the function is continuous and differentiable, then there exists a point C between 1 and alpha, such that f prime of C is equal to f of alpha minus f of 1 divided by alpha minus 1, right? So here we have used the usual formula, that is f prime of C is equal to f of B minus f of A divided by B minus A, where A is 1 and B is alpha, right? Now f prime of C can be written as C f prime of x was e raised to x minus e. So f prime of C is e raised to c minus e. F of alpha is equal to e raised to alpha. Then we have e alpha minus f of 1 can be obtained from here. So this is e raised to 1 minus e times 1, right? And this is alpha minus 1. So we have e raised to c minus e raised to alpha. Then we have minus e alpha, and here e minus e is 0. So now we are left with e raised to alpha minus e alpha over alpha minus 1, right? So now to move further, let us concentrate on this inequality, right? So here we have c greater than 1 but less than alpha. So we'll take this part. So c is greater than 1. So when c is greater than 1, we can take the exponential power here. That is, we can raise c and 1 to the power of e. So e raised to c is also greater than e raised to 1, right? So when c is greater than 1, then e raised to c is also greater than e raised to 1. And e raised to 1 is equal to e. And taking this e to the left hand side, we have e raised to c minus e is greater than 0, right? So this is an important inequality, right? So e raised to c minus e is greater than 0, and e raised to c minus e is given by this expression, that is e raised to alpha minus e alpha divided by alpha minus 1, that is greater than 0, right? Now we have to solve this inequality. Now see, here we have alpha minus 1, right? Now see, alpha is greater than 1, right? So when alpha is greater than 1, then obviously alpha minus 1 is greater than 0. So this quantity is always going to be greater than 0. And moreover, this quantity is always positive. So if we multiply both sides of this inequality by alpha minus 1, we can get rid of alpha minus 1 here, right? So we are now left with only e raised to alpha minus e alpha greater than 0, right? Now taking this term to this side, we'll get e raised to alpha is greater than e alpha, right? So this is an important result here. So now see, in our original problem, we have to prove that e raised to x is greater than e times x for x greater than 1. And here we have obtained e raised to alpha is greater than e times alpha. And alpha is greater than 1, right? So now if we replace this alpha simply by x, we have e raised to x is greater than e times x, provided x is greater than 1, right? And this is our desired result, right? So viewers, this is how, by making use of Lagrange's mean value theorem, we can prove these kind of inequalities.